Hello everyone, my name is Antoine Richard, and today I'll be presenting learning behaviors through physics-driven latent imagination. And this work was done in collaboration with Matthew Gaze from Google Brain, Stephanie ARAVECCHI, and Cédric Pradalier from the CNRS. So in this presentation, what we want to do is to deploy reinforcement learning onto robots in the wild. So on the left part of the screen, you can see our robot evolving in its environment. And usually when we want to deploy, reinforcement learning agent on these kind of robots, we have some issues. And the biggest one is, it's taking forever to collect the data. And not only because, we are evolving real time, but because, we need to deploy the robot in the field. We need to prep it to go into the field, and that's taking forever. And then we have other issues like where we need to watch the robot when it's evolving in its field and it's learning. And we need to make sure it's not going to harm the supervisor or it's not going to damage itself. So an obvious solution to that is actually to use simulation. But still, when we use simulation, it is a relatively long process. And then we have another issue, which is how do we transfer from that simulation to the real world? And with boats, for instance, can be troublesome because the dynamics are quite complex. And so something that's even more simpler than a simulation is model-based reinforcement learning. So one way to see model-based reinforcement learning is as a very simple and very efficient simulation. And in our case, and in this presentation, what we'll be doing is we'll be taking Dreamer, a very strong model-based reinforcement learning agent, and we'll be adapting it to better fit the problems that are related to mobile robots. So let's start with a quick overview of how Dreamer works. Then we'll get into the limitations that we encountered using Dreamer and how we solve them. So every time we do model-based reinforcement learning, the first thing we want to do is to learn a model of the environment. And so to do so in Dreamer, what we have is we learn what we call a world model. And so to do so, we need to learn 3 quantities. And the first one is an observation function. So in this case, we have a previous state, a previous action, and an observation, and that's going to give us a new state. We then have a transition function. So in this case, we have a previous state, a previous action, and that gives us a new state. And then we have a reward function. So in this case, we have a state, and we want to know what's our reward. So using all that, we can learn an actor that's going to interact only with that world model. And so to do so, we use that transition function we learned before. We're going to use the reward function that we also learned before, and we'll be learning a new function, which is called the value function. And so using that, we can now train an actor to interact and play with that world model. And then, in turn, we can also run that actor onto the simulation or the real world and use that to collect new data to better model the world. So when we do that, and that's what we've done on our own robot. So we train in simulation, use that world model to learn how to act, and then deploy the robot in 0 shot in the real world. And in fact, it works quite well. So when the dynamics of the robots are not really challenged, we don't have big issues. But as soon as we start to have big variances in the dynamics, then we have problems. So in this case, on the left part of the screen, what you can see is the robot evolving on a frozen lake, and it needs to break the ice. Or on the bottom part of the screen, you can see the robot with a device that's increasing its drag. So in these situations, while the robot is capable of performing its task, the performance is really way off the baseline. And what we were wondering is, okay, how can we change that model-based system to be able to adapt to new dynamics or better frame them? And so right now, the main issue is when we do imagination learning, we learn everything at once. So we learn the dynamics and the environment. And so what we'd like to do is actually be able to have environment and dynamics that are separated and be able to swap them out. So say if we take a car manufacturer is going to have a fleet of different vehicles. And all these vehicles, they are going to share the same environment. And the question we want to answer is, can we build a model that's able to change its dynamic models while preserving its environment and keeping knowledge about all these different types of models? So what we chose to do is to take this standard Markov decision process and take the state that we had before and actually cut it into 2 substates. one state would be responsible for the dynamics of the system, and one state would be responsible for the environment. And the way we would transition from one state to another is that we'd have a transition function for the dynamics and a transition function for the environment. And the transition function for the dynamics would be triggered by an action, whereas the transition function for the environment would be triggered by the dynamics itself. So in this case, we have a physical model on one side, and the other side, we have an environment model. And the way we actually give inputs to these models for the physics is that we have a GPS and an IMU, and we fuse all that using an EKF, and that gives us our observation for the physical system. And then for the environment, we use a LiDAR or a projection of a LiDAR, and that gives us the observation input for our system. And so in doing so, basically what we do is we decouple perception from dynamics. And so the way we would perform the rollouts, so the learning in the imagination is the following. So we take our robot states, so that's our physical inputs, and we embed them into a latent dynamic state. We take our perception, we also embed them inside a perception dynamic state. And then taking that dynamic state that we just embedded, we can reconstruct a physical state. Then, using that physical state and the environment state, that gives us a new latent environmental state. And using the previous environment state and the physical state, we can take an action. That action, in turn, we can use to predict the next dynamic state. And then we can iterate. So we have a new dynamic state, we get a new robot state, we take the robot state, fuse it with the environment state, and that gives us the new environment state. Then we take an action, etc., etc. And so we have this huge rollout, and then now we can use it to learn. So we can use it to learn a reward function and a value function. Value function, yes. And the way that will work is in this case, what we show is, for simplicity, we show that we use the robot state to pick an action. But sometimes the robot state would not be enough because it would not contain everything you need. So instead, what you could do is use the dynamic state. So in our paper, we use both. And so we chose to put that to the test, and to do so, we took our boat and we deployed it on a real lake. So on our boat, we have our laser, we have our IMU, our GPS, and we have two computers, one for the low-level ROS operation, and Jetson Xavier for the reinforcement learning part. And then on the left, you have the environment. So the environment is our lake, and the goal of the robot was to follow the shores of the lake. And so on this lake, we have two interesting points. So the first one is this hairpin turn, and we have then the island, which creates a narrow channel for the robot to navigate to. And that's quite complicated. So in these, what we did is we took our agents, trained them in simulation, and then deployed them in zero shot into the real world. So the upper image is the vanilla agent, and the lower image is our agent. So what we can see on the upper images with the vanilla dreamer is that what we have is a trajectory that's very windy, so lots of oscillations around, and our agent is much more steady. And the reasons for that, and we'll see that in a bit, is the vanilla dreamer tends to overshoot, so dynamics are not well understood actually, whereas our agent has a better understanding of how the dynamics works. And then if we have a look at the velocities that were reached by the robot, so in this case, the target was 1 meter per second. And what we can see is, well, our version of the algorithm was better able to maintain the velocity and had a smaller spread. So that's with the zero-shot transfer. So the dynamics of a boat are relatively complex and highly nonlinear. It was very interesting for us to see that we were able to maintain a good level of performance nonetheless. And so that's a zoom on the trajectory, and what we can really see is that our agent is much more steady in comparison to the original dreamer. So going back to the very beginning of the presentation when we said, can we actually swap robots and swap models? So in this case, what we want to do is, well, we have a boat and we also have a rover. And in simulation, we wanted to make sure that we could actually train models. So in this case, we are going to train the boat to navigate along the shores of the lake. And we'll do that in simulation. And what we'll do is we will not train in simulation the rover to do the same thing. So in this case, we replace the water by a solid surface, and we put the rover on it, and we want it to solve the same task as the boat. And these two systems, they have different action space. So the boat is driven using left-right commands, so a bit like a tank, And the rover would be controlled a bit like your car, where you give a steering velocity and a linear velocity. And so the way that would work out is we have an online learner. So this one is using the simulation, and an offline learner. So the online learner interacts with the simulation plus its world model, whereas the offline learner only interacts with the world model. Then, using the boat, we learn the environment model from scratch. So as the boat learns, we build a good and better environment model. And we use it and we give it to our rover. Then, using what we can learn the dynamics from scratch as we learn the environment, or we could use something that we already know. Say you have a very good dynamic model for a boat where you could plug it in. And same thing with the rover. So in our case, we chose to use an LSTM to model the rover, but you don't have to. You could use a standard physical system for skid steer robots. And then finally, as we learn with the boat, we collect episodes, and that gives us data to bootstrap our imagination from, so our learning mechanism. And we transfer these episodes and we give them to the rover. So that's going to help us use that to better learn. And finally, so we learn the actor online then, on the boat. And on the rover, what we'll do is that we'll interact solely with the world model. And what that gives us as a result is, well, it's not perfect. So on the right, on the left, which one? Right. On the right, you have the offline transfer. On the left, you have the online learning. So we still see that the performances are not quite as good. But what we have is a zero-shot transfer, because we never interacted with the simulation or the real environment, and the robot is able to fulfill its task. So that's a very good baseline that will need way less human supervision to go and deploy in simulation or in the field to refine. Finally, we'll be working towards the limitation of that work right now, is that, well, for now, for this to work, where we need the robots to have the same state space. So they need to share the same physical variables. But for mobile robotics, it's off, take cars or boats or vacuum cleaner. Usually they share the same state space. And then a huge assumption that we do is that the environment has no impact on the dynamics of the system. And most of the time, it is true. Well, if the car crashes into a wall, clearly that's going to have a big change on the dynamics. But at the same time, you completely failed your task. So one of the main advantage of this work is that so far when we wanted to do, well, domain randomization in model-based reinforcement learning, we could hardly do that because, well, the dynamics were embedded inside the model, whereas now we can do all that directly inside the imagination. So inside this process that generates billions and billions of trajectories, we can actually directly embed mechanism to make dynamic and very robust actors. Also, at the same time, because we have this dynamic that's decoupled, we can work towards physical models that are more transparent. So we don't need to rely on neural networks to learn the dynamics. We can use classical physical system. And finally, because we have exposed more variables within the imagination, then now we can learn to make systems that are more flexible. So we could learn behaviors that are flexible, and we could tweak the reward function on the fly directly within the imagination. So what that gives us is a very powerful tool to manipulate everything that's happening in the imagination, just like we could inside a regular simulator. Thank you for listening, and I'll take questions.
Excellent. Very great talk. Okay, so a question from the floor, or we'll go over to Jans for one from online.
Don't have any yet.
Okay, from the floor.
Hi. So you mentioned a lot of results about zero-shot transfer. I'm just wondering if you have any results, or perhaps even an intuition on how this kind of method would work if you did have like a few demonstrations or some data from the real world. And I think this is maybe related to some of the limitations you mentioned.
Yeah, so right now our main issue is collecting this data. I think we need about 5 or 6 hours of real world data, and our batteries only last 30 minutes. So, and it takes 4 hours just to put the boat in the lake. So I think it will work quite well, in particular because we can learn a better dynamic system. So right now, what's really the bottleneck is not that much the environmental model. It's really how do we model the dynamics. And if we had a better dynamic model, I don't see why we wouldn't be able to learn better. And one of the main discrepancies we see when we have these, so the difference between the performance when we transferred is really down to the dynamics between the rover and the boat are completely different. The boat tends to drift a lot. So we have a lot of drifting when we take curves, whereas the rover is ground and static. So when we start to bootstrap the imagination, we have these, a lot of dynamics that don't exist for the rover, and we try to learn an actor for that. And that's, I think in our case, what we should have done is having longer horizon of imagination and discard the beginning of the imagination. But yeah, to answer your question, I believe that if we had real-world data, we would improve the performance and because that would be direct domain adaptation within model-based reinforcement learning.
Antoine, did I hear you just say you would discard some data?
Yes. I mean,
okay, I don't know if you may have to leave the stage now. No. Okay, very bold, provocative statement, and thank you for the talk. One last question from me is I love this idea of modularizing these components, and I'm curious about automating, let's say, the choice of model as you go. For example, as you said, you have analytic models versus learned models, et cetera. So is there a method, or have you thought about the idea that you could start comparing these automatically and switching and tuning them, the choices between them? Because that seems a very interesting opportunity.
Well, for now, no. We are really trying to, I mean, we're still playing with it, trying to figure out where exactly we want to go. But yeah, it's interesting to actually let the network say, what do I want to split? Yeah. But we would need, I think Jeff Clune gave a very good example of why that would be important. Yeah. Like trying to let the simulation make weird things and see how, well, our agent could adapt to the weird things and choose which model are actually should be contained in some bits.
Yeah. Lots of interesting future work there. Excellent. Okay, thank you so much, Antoine. Excellent talk.